Hello everyone and welcome to our next lecture. So in this lecture, one of the things that I want to talk about is something called curvilinear coordinates. And the main idea behind curvilinear coordinates is giving us an alternative description of points in general it could be n-dimensional space, but we're going to focus for now on points in two-dimensional space. And we're going to see that the chain rule actually has a lot to do with really understanding what's going on here when we're doing coordinate transformations. So for a picture that I want you to keep in your mind when we're doing these coordinate transformations is we're kind of thinking of going from one description of Cartesian coordinates, x and y coordinates, and we're figuring out how these coordinates look in this new coordinate system, where you should be familiar with polar coordinates, but let's do an even more general type of mapping right here and kind of see what's going to happen. So I'm going to play the animation where we kind of get an alternative description of the plane and kind of see how there are many different possible coordinate curves that could potentially kind of pair together and describe the two-dimensional space, the Cartesian plane. So in this picture right here, we have our new coordinates, u and v. We have a u-axis, which is this blue axis, and a v-axis, which is this red axis. We see that all the points in two-dimensional space are described by their u-coordinates and their v-coordinates, similar to how the Cartesian coordinates are describing all of the points in two-dimensional space. So let's kind of dig into this a little bit and see how to better understand this. And so what I'm saying is that essentially this axis right here is the new u-axis, whereas this axis is the x-axis, the original x-axis, this axis is the y-axis. This axis right here is the new v-axis. And for any point uv, that point should map to a corresponding point in this plane. So equation-wise, what we have here is that x is going to be some function f of uv, and y is going to be some function g of uv, which we can think of as a two-dimensional mapping of points in uv space, right, into xy space, the two-dimensional Cartesian plane. So a good question that you might be asking yourself right now is, why should we consider these different new coordinate systems, or an alternative description of Cartesian space? And it's a very good question. So in general, we've seen that coordinate transformation is a very special function, a new function from two-dimensional space into itself. And these special mappings give us an alternative description of points in the space. So the big question is why? So why consider different coordinate transformations? And this is a really good question. And the main answer to this question is that very often a certain physical problem has symmetries, and we can kind of utilize those symmetries if we know how to correctly transform into a proper new coordinate system. So they allow us to simplify many problems, physical problems in engineering, in mathematical physics, in really any. There's many different areas that we have symmetries that we want to capitalize on. Furthermore, the laws of physics themselves shouldn't depend on the coordinate system in which you choose to describe them. So we have to have certain invariances in the mathematics that we use to describe the laws of physics. So what are called coordinate-free descriptions of physics are actually the correct way of describing and writing down the laws of physics. So in some sense, thinking about whether your physical laws are coordinate-free or can be expressed in some coordinate-free way is the correct way of thinking of a physical law. And this is going to be very, very useful to us and important to us when we move in the next few lectures into understanding triple integration and double integration, so multiple integrals, and how to write down certain physical laws and physical properties using the double and triple integral. And the last thing is that they have many, many other very important applications. I could spend hours just talking about all of the different applications. One of the big applications that we have of coordinate systems is to image processing. There are many practical applications. Right? One of the big applications, I could write down all of the different applications here, but that would take a very long time. An application that we'll focus on is to image processing. But there are many other possible applications. So to see this, let's consider the following picture. This is a picture of a cat named Chelsea. Don't worry, no cats were harmed in the making of this image. But what I'm going to do is apply the coordinate transformation that I just displayed for you onto this image, and we're going to see how this affects it. So you see very clearly that it's still the same image in some sense, the same image data, but as we kind of transform these coordinates to a new coordinate system, this image has a slightly different look to it, right? Because the data is in some sense moved from point to point. And so this is just one, interesting example application of one of the many ways that we can kind of use and utilize coordinate transformations. And to get an idea of what this coordinate transformation in general is doing, the most useful tool is probably the Jacobian matrix of the transformation, which is in a very real sense the first derivative of the transformation. This is the matrix, noted as J very often, and has a variety of different other notations. Sometimes we use the partial derivative symbol x, y, and then the partial derivative symbol in the denominator here, u, v. But this matrix is exactly the matrix of first partial derivatives of x and y with respect to u and v. Now it's important to write this in the correct order. The first column of the Jacobian matrix is going to be the x partial derivative with respect to u and the y partial derivative with respect to u. And second column is going to be the x partial derivative with respect to v, and the y partial derivative with respect to v. And this is probably one of the most common ways of writing down the Jacobian matrix. But like I said before, in a very real sense, this is like the first derivative of this coordinate transformation, and it contains a lot of very useful information sort of encoded in it about the first order rate of change of this coordinate transformation. Another common notation is to write this as RU RV, because if you notice the columns of this matrix, the first column is the partial derivative of the position vector with respect to the parameter u, and the second column of this matrix is the partial derivative of the position vector r with respect to v. And on this picture right here, this arrow, the cyan arrow, is RU. And this magenta arrow right here is RV. And you see that these arrows, and you can kind of clearly see that if you were to do this at any other point, the same property would hold. These arrows are directly tangent to the coordinate lines in this new coordinate system, and they're actually telling you very, very useful information about how the area is changing as you are going from one coordinate transformation to another coordinate transformation, or one coordinate system to another coordinate system. And this idea will be very, very, very useful a little bit later on when we talk about integration. So taking the double integral and later the triple integral in new coordinate systems. So when we first introduce the double and triple integral, we'll do it in Cartesian coordinates, but in a very short time after that, we'll then show how to integrate in different coordinate systems, which, due to the symmetries inherent in certain problems, is often much, much easier to do than in standard Cartesian coordinates. And what I'll do for my first example of a coordinate transformation is go over one that I'm sure that you're familiar with from your previous calc course, and this is polar coordinates. So here I have a picture of the Cartesian axis, or the Cartesian plane, and this blue axis right here is going to correspond to different possible values of the radius, r, in polar coordinates, and the red axis is going to correspond to different values of the angle. And the angle only has to go from 0 to 2 pi. This is the angle from the x-axis. And we'll see, right, what polar coordinates is doing to this, this chosen grid of values of the radius r and values of the angle theta. So this coordinate transformation is given by x is equal to u times cosine of v, and y is equal to u times sine of v, where u is the radius away from the origin, and v is an angle from 0 to 2 pi. You see that every point can be described in this way. So our radius axis, right, I can think of it, this is at u equals 0, is this blue curve right here for different values of the radius. And our v-axis is really just this point right here, which is what the point at which we're measuring the angle with respect to from the x-axis. And you can also clearly see our tangent vectors here, or the rate of change vectors for the individual coordinate directions. This is true at every single point as well. So we have this is RU, the vector right here, the rate of change vector in the direction of increasing radius, and then RV is going to be the rate of change vector at every given point in increasing angle V. So the Jacobian matrix for this coordinate transformation is going to be cosine of V, sine of V, because it's just the x partial derivative with respect to u, and the y partial derivative with respect to u. And then the next column of the Jacobian matrix is going to be negative u sine of V and positive u cosine of V, which is the x partial derivative with respect to V and the y partial derivative with respect to V. So let's see what the polar coordinate transformation is doing to an image, say, for instance. Let's take the image of the cat Chelsea, and then we'll see exactly what this transformation is going to do to this image. Along the x-axis here, I've listed the initial radius values for the image, and the initial angle values as well. And we'll go through and directly see what's happening when we apply this transformation. And what we're seeing here is a very clear picture, right, showing exactly what it is the polar coordinate transformation is doing to points in the RU, or the R theta space. The next example coordinate system that I want to show is called affine coordinates. Or an affine coordinate system. And this is a coordinate transformation of the form x is equal to a times u plus b times v plus e, and y is equal to c times u plus d times v plus f. And really what this amounts to is a stretching or a shrinking along each individual axis, as well as a translation or a shift of e along x and of f along y. So these coordinates are super useful in image processing and crystallography, and many, many different applications, but this is a very specific example. So, let's see an image, right, of what this coordinate transformation is doing in general. And so what we're seeing here is a gradual stretching, shrinking, and a rotation as well, corresponding to the chosen values of A, B, C, D, E, and F for this specific affine coordinate transformation. And you can hopefully see that this is super, super useful for image processing, because there are many times where we have to stretch or shrink or rotate an image, and if you choose the values of your coefficients correctly, you can get exactly the effect that you want while preserving certain properties of the image. the Jacobian matrix for such a coordinate transformation is going to be the following. The matrix J, which is just going to be A, B, C, D. So in this case, the Jacobian matrix is actually constant, and this gives you a number of nice properties, and allows you to do relatively straightforward calculations when you're dealing with it. The final example coordinate system that I'll consider in this lecture is called parabolic coordinates. Now, this is, these three examples that I presented are not the only coordinate systems. There are many, many different curvilinear coordinate systems, and for, I'd say, most applications, you can find a most convenient coordinate system to work in. However, polar, affine, and parabolic are three of the relatively simpler, more common coordinate systems to work in. I will post a set of slides that you can kind of read through to read about some other ones, like elliptic coordinates, bipolar coordinates. Bipolar coordinates are super useful in problems where you have, say, two poles, like magnetic fields or electric fields, so electric dipoles. But I'm just going to stick with just the three examples that I've presented so far, and parabolic is going to be the final example that I present. So this is going to be x is equal to u times v, and y is equal to 1/2 v squared minus u squared. Which means that the Jacobian matrix of the coordinate transformation is going to be v u, because the u partial derivative of x is v, and the v partial derivative of x is u, and then the u partial derivative of y is going to be negative u, and the v partial derivative of y is going to be v. So this is the Jacobian matrix of this coordinate transformation. And we expect the coordinate curves for fixed values of u and fixed values of v to be parabolas of some form. And this is exactly what we see. So this animation is showing what's happening and exactly what parabolic coordinates is all about. We're seeing the formation of these nice parabolas that are concave up and concave down, the intersection of which give us the new expression of points in the Cartesian plane. Now, I've shown a number of very kind of cool, neat examples of how these transformations can be applied to image processing, but many times, right, and I'd say more often, what we need to do, and the reason we're using a new coordinate system, is to simplify our expression of a function or of an integral or of a derivative or of a general physical equation. And what's important here is how to correctly transform and keep a function consistent in terms of this coordinate transformation. Right? If we have some function that represents, say, temperature or pressure or some physical property, we need to, when we transform to new coordinates, make sure that we're being consistent, and the function that we get in the new coordinates is giving us the same as in Cartesian coordinates or any other coordinate system for that matter. And this is where the chain of dependence for a general coordinate transformation is important. So let's say, for instance, we have some function of x and y. This can be, say, maybe, temperature or pressure. And we want to do a coordinate transformation, we ask how to transform f of xy into new coordinates u of v consistently. And the idea is that we have a chain of dependence that we have to think about here, because if f is just, for instance, the temperature, say, at a point x, y in Cartesian coordinates, the chain of dependence here is going to be that the temperature depends on x and y, and these two variables, x and y, in new coordinates u and v, both depend on u and on v. So really what we have to do when calculating the relationship between, say, the derivative of t with respect to x and the derivative of t with respect to u, and the derivative of t with respect to y and the derivative of t with respect to u, is really rely here on the multivariable chain rule. And this is relatively straightforward to go through and do. All right, we can go through and say, well, the derivative of t with respect to u from the multivariable chain rule is going to be the derivative of t with respect to x times the derivative of x with respect to u plus the derivative of t with respect to y times the derivative of y with respect to u. And vice versa, the derivative of t with respect to v is going to be equal to the derivative of t with respect to x times the derivative of x with respect to v plus the derivative of t with respect to y times the derivative of y with respect to v. And if you look at this and kind of think of what this is saying, this is directly saying the following. It's saying that the partial derivatives of the temperature in the new coordinates u and v are directly related to the Jacobian matrix of the coordinate transformation, as well as the partial derivatives in the original space. So using this chain of dependence allows you to, say, convert from the polar derivatives to Cartesian derivatives, or say the derivatives in the parabolic coordinate system, and see the relationship between those and the derivatives in the Cartesian coordinate system. So this is a very, very big idea and very important to think about when you're, say, calculating partial derivatives. Another way of going about this for simpler coordinate transformations is just thinking of, well, if our temperature is this function f of xy, and maybe I will change this function to be a different name, because we already used f and g for our coordinate transformation, so that's probably the best thing to do here. So I just changed the temperature function to be h, because we already introduced f and g as our general coordinate transformation. So under this coordinate transformation, where x is equal to f of u and v, and y is equal to g of u and v, right, t is going to be our function h, which is the temperature function, evaluated at f of u and v and g of u and v. So in order to get the temperature function in the new coordinates, you simply have to plug in your x coordinate and your y coordinate as functions of the new coordinates. And this will give you a consistent, correct temperature function in the new coordinates. But this is a very, very useful idea and a useful tool. So for an example of this, let's go through and consider the standard function that we've been talking about a lot for our examples, because it's not too complicated, but it's complicated enough that it gives us a very nice picture of many different examples for many of the concepts that we want to kind of investigate. Let's look at the function x times y times e to the negative x squared plus y squared in polar coordinates. And I'll just use the example of temperature. You can use really any physical example that you like to kind of think of this in applications. But the idea here is that in polar coordinates, where x is r cosine theta and y is r sine theta, we have that this t is going to be r cosine theta times r sine theta times e to the negative r cosine theta squared plus r sine theta squared. And you might ask, well, this is a lot more complicated than the function that we started with, but we do see some simplifications here. The first simplification is to rewrite this as r squared cosine theta times sine theta, and then e to the negative r cosine theta squared plus r sine theta squared is going to simplify to just e to the negative r squared, because cosine squared of theta plus sine squared of theta is equal to 1. So we have this nice function here now that's a product of a function of r and a function of theta. And if we were to go through and compute the partial derivatives of this new function with respect to r and theta, you could go through and do that consistently and nicely. And you can also, even in general, using the relationship that I described before, show the direct relationship between the x partial derivatives and the y partial derivatives. But let's just go through and do this. When you take the r partial derivative here of this function, so dt dr, this is going to be equal to negative 2 times r times r squared minus 1 times e to the negative r squared times sine of theta times cosine of theta dt d theta is going to be r squared times e to the negative r squared times cosine squared theta minus sine squared theta. And if you go through and compute, say, the critical points of this function in this new coordinate system, you'll get this exact same 5 critical points that we solved for earlier for this function, which basically, when you kind of look at this, you solving critical points, set the dtr and dt theta simultaneously equal to 0, you're going to get that the correct critical points directly correspond to either r equals 0, which is the origin, or r is equal to 1, and theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. which correspond directly to the critical points that we solved for before. For this function when we investigated it in Cartesian coordinates. So I think this is a really neat and illustrative example, right, showing that it doesn't matter in some sense what coordinate system we use as long as we're consistent with our mathematics.